Hello. I'd like to talk a bit about how Rust can be used on embedded systems. And the way I'm using it is usually using the Riot operating system. This is an update on something I've talked about almost 5 years ago here, back when that whole project started. It's now in a well better shape, and yeah, let's jump right into it. First, when I'm talking about embedded systems, what I mean, I'm talking about what ITF documents typically call them constrained devices. So this is the typical, say, what you typically get nowadays in the Arduino devices. So 10 kilobytes, maybe 100 kilobytes of ROM and RAM. Cortex M3 is a popular architecture. This is powering the later Arduino models. RISC-V is also becoming more and more common. In practice, developing there means that you don't have all the nice features that you have in a modern operating system. So usually you may or may not have dynamic memory management. Most of the things that you actually need are allocated statically or on your stack. There are a few startup things to be concerned with. For example, if you're bringing up the device, it doesn't initialize its own RAM, so someone has to do that for you. And there are linker scripts to keep track of, and you don't just copy files over. You usually have a debugger connected that sends the software over to the device. When you want to use Rust on such a device, you have a few options. The first, that is also probably most familiar for those who've worked with microcontrollers before, is to just use them bare metal. That is, there's no operating system involved. You don't have any big framework. You just write code that executes on the device, and whatever the device can do, you can do. There are tools to help you with that that make this a lot easier to work with. On the stacking up, there's usually one crate that provides some runtime environment. I hope I've updated this correctly, and it's still Cortex M3 MRT crate. This takes care of things like initializing your memory in the first place before you can assume that something is serial initialized and stuff. That also copies static variables that are initialized from your ROM into your RAM, that kind of things. And then crates build up on that, and on the lowest level, they are using the hardware description that nowadays the vendor provides to give you register descriptions that you can use according to the datasheet. So for example, when you have a microcontroller that has a serial line connected, a serial peripheral connected to it, then this has a register bank in which you can place the data to be sent or read the bytes that are received. And this maps the registers that are defined with some address number to nicely usable names and gives them all the properties to read them atomically and so on. Building on that, you often get device driver crates. So in the Raspberry Pi, in the Raspberry, what's it called, Pico example, you have a crate that does the peripheral wrapping, and then on top of that, a hardware abstraction crate that implements actually useful functions, like send a series of bytes to that through that hardware channel, or set this or that GPIO pin, initialize those pins, that kind of operations. They are often expressed. I'll come back to that. And when you're having an actual board, you often have concrete attached hardware devices. For example, one pin of your microcontroller might be connected to an LED. Then there is a description often in a dedicated set of crates that gives you an abstraction of an LED there instead of an abstraction of a GPIO pin. So you can turn the LED on and off instead of pulling a pin to a high or low voltage, and then you will still have to know what is on, what is off. The last one of those are also those, if you're getting started on that track, that give you good examples. So for example, in the RP Pico, in actually most of the board support crates, you will get some example called Blinky that just makes an LED blink. So that makes it way easier to get started. The second option, and more and more popular, especially looking back at the last time I was here, option is to use full operating systems written in Rust. There are not always operating systems in the sense that, I mean, they're never operating systems in the sense of Linux, because those devices are just too small to provide all the capabilities that desktop operating system provides. But some of them even don't resemble so much the other embedded operating systems, but they just provide the very minimal frameworks that you need to build your applications. One that I would like to highlight here is Arctic, formerly called RTFM, until some suits showed up and said that, yeah, you can't have fucking in your de-abbreviated name, so it's Arctic now. It also meant real time for the masses, but who knew that? This is an, I'd say, operating system that implements all those task switching and concurrency primitives, not in terms of explicit process switching, but in terms of using interrupt levels. So it's rather specific to hardware that is built similar to ARM Cortex devices, although I think it works on other hardware these days as well. But it gets it takes a bit of getting used to from its whole style. Embassy is another framework. If you're more into asynchronous programming, then this has you covered and provides an embedded suitable runtime, and also some of the hardware abstractions that are otherwise found if you're in the bare metal environment for the particular boards. And there are others. So back in 2018, the reason why I didn't go that path was that the hardware support was just not there yet. There was too much missing, also in terms of networking. There were libraries, but they didn't compete with RiotOS. The situation has improved a lot. So the hardware support has grown better, and there are now networking libraries that are written in Rust that are much more capable than back then. But given that embedded devices often come with a whole set of networking primitives around, especially for mesh networking, that's still not all covered to the extent that I needed. So the third option is to use an operating system that has been around, in this case for over 10 years by now, RiotOS, which is written in C. As the others, it's not an operating system like Linux, but it's using it's providing typical basic functions. It's providing memory management, some process management, concurrency for the processes, and all the messaging primitives. But it doesn't use anything like dynamic linking. So all the program is built into a single binary, as is with most of the other examples here, and executes that as a single entity. It has a large community that has been meeting for several years in a row in summits, and it has something like 200 different boards, embedded development boards supported. So it's a good starting point. If you have embedded hardware, if you have any embedded hardware, chances are you can just run Riot on it. So the question is, one question you could ask yourself is, what do you really want to pick? Well, the point that I'd like to make primarily here is that it doesn't matter too much, because unlike in C, where you typically have libraries that describe their own hardware abstraction layer that you could then implement for your peripheral. In the Rust embedded ecosystem, there's a crate called embedded HAL, embedded hardware abstraction layer, and all those distinct device driver crates don't implement their own types. They all implement their own types for I2C, SPI, serial devices, etc. But those types are not used directly, but usually through those traits. And for RiotOS, the same traits are implemented. So if you have a program that, say, talks to your custom sensor devices and through a serial line and maybe a few GPIOs, porting that program over between Riot or Embassy or bare metal doesn't make too much of a difference from the program's point of view, as long as it doesn't use more internal components of the operating system. Looking at the things that we have in Riot, this image is a bit older. So back in, yeah, this is a general overview of the components of Riot. So there are support for different hardware types. There is support for a whole bunch of typical peripheral components. There are different network components further on the right, and there are also high-level abstractions like sensor data reading, shell, etc. We can build applications on that because there are Rust bindings for Riot, and the amount of API surface that has been covered in that is accessible with Rust abstractions has been growing over time. So this is the picture of 2018. I haven't found time to update this to the latest state, but like DACs have been added, timers, flash writing has been added, if I remember correctly. More kinds of networking are accessible. So this is growing and growing, and it's also easy to extend because basically all one has to do is decide how that API would look like in Rust and do a few unsafe wrappers. This is also a picture from back in 2018, and I think it's a good thing that this practically still looks the same. What did change is that it didn't say it explicitly here, but back then this was all depending on nightly and ton of patches here and there, and nowadays this has been working with stable Rust for I think 2 or 3 Rust releases, and doesn't look so much different from using Riot with any other language. Program-wise, this has also not changed, which means that I hope I've done a good job with the API design. You write your main function as you do in a big operating system program. All you have to do is introduce to Riot that this is actually your main function, because there is a bit of wrapping going around there, but not too much actually. And yeah, that's I think the point I made before about those abstractions is that this and all basically everything from this line on, if you switch over to any other tool that you're using with Rust as a baseline operating system, will look the same. You just exchange that type. You exchange the initialization, because maybe if you're running this on Linux, and you definitely can, your I2C device will not be called 0, but dev I2C3, for example. But that's about the difference. This is also a slide that I picked from a few years ago. We used to have lots of issues because Riot does not have a pure symbol or library-based API, but has a lot of inline processing. Yeah, it still does. But now there is C2 Rust that does a bit of transpilation of the trickier components of the C code over to Rust. This also helps with the need for constant propagation that is fundamentally working, but not in the setup we're using it with Riot yet, because there's a lot of GCC involved. So that is still around, but mitigated, because we can just take C functions, transpile them over, and that happens transparently in the crates that are provided. The API mappings, yeah, they are still incomplete. Riot is a 10-year-old project that has, I think, about 100 contributors, excluding very small ones. So it's a lot of API service to cover, but the important parts are growing and growing. And it has caught up, and it has gathered a few more users since then, because given that it has been in mainline Riot for about 2 releases, it's well usable now, and and people are starting to pick it up. Yeah, if you want to give it a try, it's described in the Riot documentation on the website how to get started. If you don't want to install everything, there is a Docker image that you can use and set the makefiles on. And yeah, that's it from my part. And I'm happy to take questions. So the question was why I'm using a macro here instead of an attribute macro. Back when I wrote it, that was the style that also the Cortex-M runtime used. So I mimicked that. Could just as well be an attribute macro as well, yeah. But this is 3 lines of code. This is about 3 lines of code behind it, and the attribute macro would be more. Thank you.